Hey there and welcome. Today, we're jumping into a classic problem, finding the area of a triangle. But we're not just sticking to the easy stuff. We're going to master any triangle, even those really tricky ones. So, what happens when the one thing you think you need, the height, is totally missing?
We all remember this one from school, right? Area equals 1/2 base times height. Super simple, works like a charm, if you actually have the height. But what if you don't? What if all you've got are the side lengths, or maybe a couple of sides and an angle? What do you do then?
Well, that's exactly what we're here to talk about. We're about to add two super powerful tools to your math toolbox. Seriously, these are the formulas you're going to use in Precalculus and way beyond to nail those kinds of problems every time.
Okay, let's grab our first tool. It's the sine formula. Think of this as your secret weapon for a really specific but super common situation. You know two sides of a triangle, and you know the angle that's tucked right in between them.
So here it is. Area equals 1/2 A times B times the sine of angle C. Now listen up, because this is the key part. That angle C has to be the included angle. You know, the one that's literally sandwiched between sides A and B. That special setup, side, angle, side, is why you'll hear this called the SAS case.
Okay, seeing the formula is one thing, but math is all about doing. So let's actually put this thing to work. Let's say we've got a triangle where side A is 8, side B is 6, and that all-important angle between them is exactly 30 degrees. All right, let's walk through this. First step, we just lay out our pieces. A is 8, B is 6, and our included angle C is 30 degrees. Perfect. Step 2, we just plug those numbers right into the formula. So area equals 1/2 times 8 times 6 times the sine of 30. Now, if you remember your unit circle, the sine of 30 degrees is just 0.5. That makes our math really easy. It's just 24 times 0.5, giving us a final area of 12 square units. See? Not so bad.
All right, tool number 1 is in the bag. But what if you don't have any angles at all? What if you walk up to a problem and all you've got are the lengths of the three sides? For that, we need a totally different kind of tool. And that's when we bring out the big guns, Heron's formula.
Now, I know this one looks a little scary at first glance, but trust me, it's actually super clever. The area is the square root of, get this, S times S minus A times S minus B times S minus C. So the obvious question is, what on earth is S? Well, S is just the semi-perimeter. All you do is add up the three sides, A, B, and C, and chop that number in half. That little S is the key that makes the whole thing work.
Let's do an example to make sure this makes sense. Imagine a triangle with sides that are 4, 13, and 15 units long. We don't have a single angle to work with, which means Heron's formula is exactly what we need. Okay, first things first, we always have to find S. So we add them up, 4 plus 13 plus 15, that's 32 divided by 2, and we get our semi-perimeter. S equals 16. Awesome. Now we just plug everything into that big formula. We've got the square root of 16 times 16 minus 4 times 16 minus 13 times 16 minus 15. So that simplifies down to the square root of 16 times 12 times 3 times 1. And when you punch that in, you get a really nice clean number, 24 square units. Done. So now you've got these two fantastic tools. But just like with any powerful tool, you got to know how to use it right. There are a couple of common traps people fall into, so let's make sure you know how to avoid them. You could think of this as the how-to guide.
With the sine formula, the number one mistake, hands down, is using the wrong angle. Remember, the formula only works if the angle is the one included, the one literally stuck between the two sides you're using. If you grab another angle from the triangle, your answer is going to be wrong. So always check for that side angle side pattern.
Okay, and for Heron's formula. The mistakes usually happen with that S value. First off, people just forget to calculate it. It has to be your very first step. Second, they mix up perimeter and semi-perimeter. Remember, you have to divide by 2. And finally, just be careful with the subtractions inside those parentheses. It's so easy to make a small mistake there, and it'll mess up your entire answer.
So you might be thinking, okay, cool formulas, but is this just for a test? And the answer is a big, fat no. These tools are used all the time to solve actual, real-world problems, especially in situations where you can't just, drop a measuring tape down to find the height.
Let's take land surveying. Imagine a surveyor out in some big, uneven field. It's pretty much impossible for them to measure a perfect, straight-down height of a weirdly shaped piece of land. But you know what they can do? They can measure the lengths of the sides.
And with Heron's formula, that's all they need to get a super precise area for selling the property, figuring out taxes, you name it. In fact, let's try one of these problems right now. Put on your surveyor hat. You've measured a triangular plot of land, and the sides are 120 meters, 150 meters, and 200 meters long. So, which tool are we reaching for? Well, we've got 3 sides and 0 angles, so it's got to be Heron's formula.
Okay, let's crunch the numbers. Step 1 is always sums. So 120 plus 150 plus 200, all divided by 2, gives us 235. Now we plug that into the big formula. After we do all the math, we get a pretty big number, about 8,950 square meters. Now, in the real world, big plots of land are often measured in hectares, so let's do a quick conversion.
And there we have it, our final answer. The total area is roughly 0.895 hectares. Think about that. That's almost a whole hectare of land. And we calculated it perfectly without needing a single height measurement. Now that is the power of having the right tools.
So, quick recap. You've got 2 sides and the angle between them, use the sine formula. You've only got the 3 side lengths, Heron's formula is your best friend. The point is, you are now officially equipped to find the area of any triangle that gets thrown your way. Which leads me to a final question for you. If you can break any complex shape down into a bunch of triangles, what kind of massive, complicated areas can you figure out now? That's where things get really interesting.